Today we are joined by Dr. Zoe Chan. He's going to be talking to us about the association between hoof asymmetry and movement asymmetry in racing thoroughbreds. And Zoe is currently a postdoctoral fellow here in the Faculty of Kinesiology at the University of Calgary, and she's currently working in Dr. Tito Fow's quadrupedal biomechanics lab. She also did her PhD here at the University of Calgary, also in the Faculty of Kinesiology, specializing in wearable technology, and specifically the biofeedback of gait retraining under real-world running conditions. And she did that under the supervision of Dr. Reed Ferber. And an interesting fact is that she takes coffee fairly seriously. She has, in fact, 6 different ways to make a cup of black coffee at home. Maybe you can ask for that.
Hey. Thank you for the introduction, and thank you all for being here today. This is actually my first time presenting at an HPL seminar, so I'm really excited to be sharing the findings of this project with all of you. In this project, we looked at race horses, and we looked at the relationship between the direction of training, hoof asymmetry, and movement asymmetry. If you have been to a racetrack before, or you've watched horse racing, you would know that horses runs around in a loop. So when horses goes around in a loop, they can go in one of 2 directions, one of which is counterclockwise. So when the horse approaches the curve, they turn left, and that's a counterclockwise track. In North America, most of the tracks are designed as counterclockwise tracks. And in other places around the world, some horses race clockwise, so they turn right when they approach the curve. Now, there are some areas in the world like UK, Japan, Australia, where they have tracks of both racing directions. But even so, for an individual horse, most likely that horse is trained and raised in one direction throughout their whole career. Our research team is particularly interested in looking at how this type of training, namely like training in one direction, would affect a horse overall. Now, horses are like human, they have natural gait patterns. But unlike human, where we either go walking or running or sometimes jogging, horses has 4 natural gait patterns. And in the order of increasing speed, those patterns are walking, trotting, canter, and gallop. Walking and trotting are symmetrical gait patterns, meaning that that limb pattern on the left side will be repeated on the right side after half a stride cycle. And that works for walking and trotting. Canter and gallop are asymmetrical gaits, so that the things happen on the left side, the fore and the hind won't be repeating on the other side. Today we'll focus mainly on trotting and galloping. In a trotting gait, trotting is a rapid symmetrical diagonal gait. So when they first land on the ground, it would be a diagonal pair. In this case, would be the left hind and the right front. After these 2 land, going through stand space, push off, then all of the legs will be off the ground. In that case, is the aerial phase, which is also known as the suspension. After that, the other diagonal pair is going to land, go through stand space, push off, and then in an aerial phase again. And that completes one stride cycle. And it just gets repeat and repeat and repeat, like a human running or a human walking. So for gallop is one of the fastest gait among the 4 of them. Well, gallop is the fastest gait among the 4 gait patterns. And in gallop is a asymmetrical gait. All the hooves lands at different time, and all the hooves leave the ground at different time. One footfall sequence is that they first land with a left hind foot, and then the right hind, followed by the left front, and then the right front. And then they will each leave the ground, and then it will be the aerial phase. It gets repeated, 1 stride of gallop, 2nd stride of gallop, 3rd stride of gallop. Now, depending on which limb leaves the ground last, like the one right before the aerial phase, that determines which leg is the leading leg. So in this gait sequence, where the right forelimb leaves the ground last, we call that the right lead gallop. And the right forelimb is the leading limb. The idea of having a right lead gallop is that we have the mirror of it. So we have the left lead gallop. which is just the opposite, the mirror of what's happening in a right knee gallop. So starting with the right hind, and then it goes to the left hind, right front, and then the left front, and then going to the suspension phase. Now going back to horse racing and horses running around a curved area, this is a slow motion video that I took a couple months ago in Leduc. We were watching a group of horses going training in the morning. We were standing really close to the bend, and I took this slow motion video. After rewatching it a few times, what I realized is that they actually changed their lead. So once it loops back, you will see that along the straight stretch of the track, they are using a right lead. What that means is that their the right forelimb was the last to leave the ground before the aerial phase. But as they approach the bend and they start turning left, they actually switch to a left lead. I was fascinated by this because 1 year ago, I was studying human running for like 8 consecutive years, so I don't see lead changes at all. But I see this video and I keep watching it and keep telling people how fascinated I am. Well, this is why I put it here. But the second reason why I want to put up this video today is because I want to show you that there are adaptations that are in a horse locomotion or biomechanics that help them turn a bend. So the horses is doing something different when they are turning than when they are running on a straight stretch of the track. So other than lead change at gallop, other researchers have also found differences when a horse is running at a curve or when horses are running along a straight line. One of which is that they found a change in speed when the horses run around a curved area. So this study, published in 2011, measured the racing speed of some winning horses in the UK. If you reference that position graph on the left there, you see that as the horse is turning around the corner, their speed also significantly reduced. And if you look at the blue line, where the turn is sharper, there is an even further reduction in speed when they're turning a sharper corner. And this is not only found in horses. In human sprinters, they also found the same thing. When they go around a curve, they tend to slow down, and sharper the turn, they further slow down their running speed. Another observation for horses going around a corner is that they tend to lean towards the center of the circle, so the inner bank when you're running around an oval track. Again, this is something that is also being observed in human sprinters. The idea of this is to put that center of mass closer to the center of the circle, so that the normal ground reaction force and the moment from the centripetal force can balance each other out. And this is one of the things that has been observed in horses going round and round in circle. Now, when you look at these three things, they kind of explain the whole horse in a general, like the whole horse altogether, a whole horse. What about the difference between the left side and the right side of it? There are also studies that look at the inside and outside limb in different way and compare them. What they found was that the inside leg, which is the one closer to the center of the circle, has been shown to have a shorter stride length, longer duty factor, and a lower peak vertical force. The same study, the one quoted as number 3 there, also found that there is a difference in the moment along the longitudinal axis. But what they found was that this moment suggested that the compression force for both of the limbs were larger on the inside of the circle. Now, if you just look at this, it would be like, yeah, it kind of like the same between the inside and the outside. But if you think about the direction that they are going, the side that has the increased compression force, which is the one closer to the circle, is actually the lateral side of the inside limb, but the medial side of the outside limb, suggesting that there is a difference in the loading pattern between the outside and the inside limb. Now, all of this happens when the horse is actively running around in a circle or they are going around the curve. This project that I am presenting about today is more on what other midterm or longer term effects. So are there any difference in them other than when they are actively turning or running around in circles? And that brings us to the first part of our project, And in this project, we compared the movement asymmetry between two groups of horses. So altogether, we have 300 race horses. Around 150 of them were raised and trained in Singapore, where they have a counterclockwise track. And the other half of the race horses were raised and trained in Hong Kong, where they go around in a clockwise manner when they are training and racing. We trotted both group of horses in a straight line and compared the force between the inside and the outside limb. Based on the study, what we found is that in the Singapore group, so the group that usually go around counterclockwise, we found that the right side has reduced force during their standstills. For the group from Hong Kong, we found that the left side has reduced loading. Now, if you consider their predominant training racing direction here, you will find that both of the sides that were found to have reduced loading are the ones that would have been on the outside when they are running around in a circle. And that's what we conclude from this part of our study, is that there is a reduced loading in both the forelimb and the hind limb when they are trotting in a straight line, but that limb corresponds to the outside limb when they're going around in their predominant direction. So for the next part of our study, we want to look at the hoof-shaped asymmetry. Because from the first part of our study and other previous study, we learned that there is a difference in the loading pattern between the inside and the outside. And we know that hoof shape is adaptive to loading. So the difference in the amount of force given to the left and right would eventually change the hoof shape as well. One common method of quantifying asymmetry in hoof shape is to measure the hoof width and compare that between the left side and the right side. And there has been a previous study that suggested that a narrower width is associated with increased movement asymmetry. And that brings us to part 2 of our study, where we looked at a group of race horses that predominantly train in one direction and see if there is a left-right hoof asymmetry. So to do that, we had 186 thoroughbred race horses that train and race at the Hong Kong Jockey Club. So they are used to a clockwise training. They were all clinically sound within 6 months of data collection. So at the end of their shoeing cycle, immediately after we removed their horseshoe, we took a photo at the bottom of their hoof using this app called Cam. We took these photos from all of the limbs, so left, right, forelimb, and hind limb. And then we used a program called Neutron Hoof to process these photos. It starts with calibration. All of these photos come with a finger clip. And because we know the exact length between the two markers on the finger clip, we're able to get the pixel to millimeter ratio, which will allow us to be able to measure things that are on the photo on the same plane. So assisted with the image processing software, the first step that we do after the calibration is to find the midline of the hoof, which is also the axis of the frog. So you basically split a hoof into a left half and a right half. So draw a line between here, and then using a perpendicular line to find where the widest part is. So the widest part of the hoof, perpendicular to the frog, is defined as the hoof width. We got the hoof width from all 186 race horses and all 4 of their hoofs. After gathering that data, we were able to run a pair t-test between the left side and the right side. What we found is that there is a significant difference between the outside and inside limb for both the fore and the hind limb. And looking at the average between the left and the right, we found that on average, the right side is wider than the left side hoof. So with that, we want to look a little bit further, which moves us on to part 3 of this project, where we look at movement asymmetry between 2 groups of horses. So these horses are within the same cohort that we used in part 2. It's just that we want to divide them into those who have a wider inside hoof and those who have a wider outside hoof. Our hypothesis for this part of our study is that for those who showed asymmetrical forehoofs, we expect to see movement asymmetry in the pole and the withers. And for those who have asymmetrical hind hoofs, we expect to see movement asymmetry in the pelvis. So before we can divide them into this group and that group, we need a threshold to say that, oh, they are in fact asymmetrical. So what we did with that is that we take the whole cohort and then we calculate the absolute difference between the left side and the right side. And using the median, we determine the threshold. Threshold for a full limb asymmetry is at 5.3 millimeters, and threshold for hind limb asymmetry is at 4.2. So if the left-right asymmetry for that horse is below this number, then they are considered to have a balanced left-right hoof and would not be included in this part of the analysis. We did find 33 to 35% of horses having wider inside hoof, which is their right side, and then a 15% of them having a wider outside hoof. And then we compare the group with wider outside and then the wider inside. We performed gait analysis on all of the horses. We put inertial measurement units along the midline of the horse. So we put it on the pole, the withers, and the pelvis. These IMUs were set to collect triaxial linear acceleration and angular velocity samples at 60 Hertz. So after the horse is prepared, we trotted this horse in a straight line on a firm and level surface. So they go back and forth until we collect 15 to 30 strides per horse. So data from the IMU were then processed. The first step we do is to segment the full stream into strides, into different individual strides. To do that, we took the pelvis mounted sensor. We integrated the vertical acceleration to obtain the vertical velocity. And we also checked the roll data from the IMU. So how we determine a foot contact is first we find the local minima of the roll. So we identify this point. And then from the vertical velocity, we also find the minima, which is right before the minima of the roll. So that point is defined as a left hind foot contact. Once we know all the time points where the left hind foot contacts are, we are able to segment the whole data stream into individual strides. We then took the vertical acceleration and did a double integration to get the vertical displacement. So this is a sample of what the pelvis vertical displacement looks like. We trotted the horse. So if you remember, trotting is diagonal pairs. So it starts with a left hind foot contact. So it goes down in the mid stance and then goes up in an aerial phase, and then the other left hind, right hind. The other pair lands on the ground, mid stance, push off, and then go up again and then down. So it repeats itself. What this means is that the two peaks are the furthest position that they go up during that aerial phase. The two troughs corresponds to when they are at their weight loading phase, so the lowest point that they get. The three parameters that we are especially interested in are maximal difference, so the difference between the first peak and the second peak, the minimal difference, which is the difference between the two troughs, and then the upward amplitude difference, which is just the range between the lowest point to the highest point between the first half and the second half of a stride cycle. We calculate all three of these variables from all three of our sensors. So altogether, we have 9 different variables. And here's what we found. When we compared the group of horses with a wider inside limb with those with a wider outside limb, what we found is that we found a significant difference in their up diff and also a significant difference in their max diff. So that we know these two groups of race horses are moving differently. But when we look at the average of the up diff and max diff between the two groups, one of them is at a positive level and the other one is at a negative value. What a negative value indicates is that there is a larger displacement in the pelvis of that horse, or in this case, because it's the pole, it's the larger displacement of the pole on the left side after that push off. So if you group all the results all together, what this indicates is that there is a larger vertical displacement at the pole. Doesn't matter whether the wider side is on the left side or the right side. When between the midstands to the top of the aerial face, after that wider side push off, you see a larger vertical displacement in that half of the stride cycle. As for the max diff, it indicates that a higher vertical position of the pole was being reached after the wider side pushed off as well. And when we looked at our values from the withers, it shows a very similar pattern. We also found significant difference in the up diff and max diff between the two groups, which indicated that there is a larger vertical displacement whenever the wider side push off and a higher vertical position of the withers reach after pushing off from the wider side. And now let's look at the group with hind hoof difference. We didn't see any significant difference in the up diff, max diff, nor the min diff. So there were the movement pattern were comparable between the two groups. And to kind of summarize between the part 2 and part 3 of our studies, what we found is that in this group of racing thoroughbreds that predominantly train and race clockwise, we found significant difference between the left and the right hoof. And the average between the left and right suggested that they have wider right side hoof in both forelimbs pair and the hind limb pair. We also found more horses with wider right hooves than left hooves. And from our movement symmetry calculation, we found that horses with a wider forehoofs, which are the 30-something%, so the bigger majority of them, shows a larger vertical displacement during and after push-off. And for those who have a wider left hoof, we see this when the left side push-off. We didn't see any significant difference in the pelvis, vertical displacement between the group with wider left or right hind hoofs. So how is our result useful? Well, we hope that our findings is useful for farriers. Farriers are the professional who goes and take care of the hoofs of the horses. They trim them, they put shoes on them, so they regularly look at the hoofs of the horses. So we hope that farriers, because they keep a regular monitoring of the hoofs, they would be able to see different changes in the hoof width and the difference between the left and right. And together with some movement asymmetry data, they might be able to target a balanced force production by minor adjustment in the hoof width. Secondly, we also hope that our findings can be useful for vets, especially when they're doing lameness assessment. Lameness is defined as an abnormal stance or gait in a horse. The reason why a vet has to routinely go and check on these racehorses is because, unlike human, they can't tell the physio and they can't tell the doctor that they're in pain. So these vets have to go to the horse, see them trot, which is very similar to the protocol that we had in part 3, just trotting them up and down. The vet is looking at the vertical displacement of the head, withers, and pelvis. So basically qualitatively measuring min diff, max diff, and up diff, because these can indicate different types of injuries or disease that are within the horse. For example, if they see a difference in the min diff, or like the lowest point that they get between a right hind and a left hind difference, would indicate a difference in their weight bearing phase. And for the difference in max diff would indicate a difference in their push-off phase. So these might indicate or tell the vet something is going on and what might the problem be for further analysis. Also, because all the horses within the part 3 of our studies are clinically sound, we still found movement asymmetry in this group of racehorses, suggesting that sometimes we're not looking exactly at 0% difference between the left and right. So especially in racehorses, they need to adjust that lameness or clinically significant threshold for suggesting that horses would require for an assessment. And of course, this study is not without limitations. For the part where we compare the left and right hoof, unfortunately, that part we did not have a control group which predominantly trained in a straight line or a group that run in the different direction to compare to. So we cannot rule out that there may be behaviors in the horse that would change the hoof width that is irrespective of the training direction. And secondly, for the whole project, because it's a cross-sectional study, so we are able to establish a causal relationship between the way they train, the hoof shape asymmetry, and movement asymmetry. But what we know is that there is a relationship between the hoof shape asymmetry and the movement asymmetry. So if we can design interventional studies measured before and after trimming and see if that would change movement asymmetry, or we can have a group of horses training in the other direction for a couple of weeks and we measure these, then we will have a better understanding of this interconnected relationship between these three factors. And in the future, we will be looking at other external hoof characteristics as well. We did not only take photos of the bottom of the hoof, we also took photos from the lateral side and the frontal side, which would give us a lot more information for when we compare if the left side or right side of the hoof are symmetrical or not. We're especially excited to look at the dorsal hoof wall because it has been suggested that a difference in that can change the force vectors in the sagittal and frontal plane. Another direction that we would go is that we will be measuring horses when they go around in a circle instead of just trotting them in a straight line. Because it has been shown that when horses go around in a circle, some of these movement asymmetry get amplified. And we also want to see if that would change on different surface, like between turf, sand, and rubber surface as well. And again, I would like to take this opportunity to thank my supervisor, my wonderful teammates, and a group of research students who helped us look at all 1,000 hoof photos to make sure that this project is valid. Thank you.
I might have missed it. So you found asymmetry in the load, and then you found asymmetry in the width of the hoof. So did you try to correlate the load, like the ones that have the lowest load, have the lowest hoof size, or like did you try to correlate between load and the size of the hoof?
That would be a very interesting thing to do with our study. But for now, I have only like classified them into like a wider outside and wider inside and then compare between the two groups. It might be interesting to actually do a correlation, but a guess would be like the ones in the middle, which have very balanced ones, would not be showing us a lot of differences in the movement asymmetry. But we do have all the data that we can do the correlation.
So do you think there is a correlation between the load and the size of the hoof?
Yes, so based on like a dichronomous like difference between the two, we did see that doesn't matter which side it is, the wider it is, the more difference there are, and they are on the side which is wider. So we do we would hypothesize based on that there would be a correlation.
Do you have any race data from those horses that you tested to see how they like ranked overall throughout the season? Because it'd be interesting to see if the ones that had less asymmetry were actually worse.
Yes, we do have the race data. They are all public. So because people like bet on race horses, so all of the race data, how many like races they did, what is their finishing time, are all online. I just need to find the time to actually download that and put it into like a way that I can analyze it with our movement asymmetry. But based on previous data, because they are all clinically sound, the more movement asymmetry between the horses doesn't mean that they are worse in performance. So there may not be a relationship between the two.
I think you had a question, right?
Oh, myself?
Yeah, earlier, yes, but actually just on instance.
Okay, perfect. Then Jackie and
I was gonna ask something similar to Andrew, but I'll ask from more of an injury standpoint. So is it the limb that is undergoing this higher load and the hoof adaptations? Is that the limb that's getting injured or?
We need like large scale epidemiology data to actually see if like racing in one direction or the other, kind of like put a certain limb at a higher risk or not. If I remember correctly, in the Hong Kong ones, the inside limb injured more. No one correct me, I think I'm right. In that case, this could be because they are putting more force in it, which we would see from the movement asymmetry data. But there are also other data suggesting that the outside limb is having a higher vertical load. So we don't know the exact relationship between the peak vertical force and injury, but there is a directional pattern of injury within horses that train predominantly in one direction. What?
Yeah, so my question was, how in your studies, how do you control for the fact that there are differences in the horses? Are they all specific sex / gender, or are they like how old are the horses? Like what age are they? How long have they been on the track for? Do you control for those factors there?
So within the 186 horses we have, they're all geldings, so they're of the same sex. They're between age 3 to 10, so they're in their active racing career. And because they got taken care of pretty frequently, so a farrier would go to them every 3 to 5 weeks to have their hoof trimmed, so they have a similar care and similar routine within the whole cohort.
And so, is it me?
You can go ahead.
Oh, I didn't hear.
That's okay, go ahead and then
Go
write that.
go ahead, go ahead.
It plays off of his question. Did you look and see if age influenced the difference between the asymmetries and the hooks?
For this project, we didn't, but we foresee that this asymmetry gets built up across time. So perhaps their length of training or how much mileage they accumulated so far would perhaps change the amplitude of the difference in movement asymmetry. So I will go back, look at the racing years of these racehorses and see if we can find something.
I think it would really strengthen that argument that it's an adaptive kind of response, because you'd expect the older ones that have trained and raced for longer periods of time, so.
They did, yeah.
You said something that you had a few different take-home points. You said horses that train clockwise have wider hoofs on the right side. Okay,
Wider inside, yes,
right, wider
inside. This
inside,
clockwise, so the inside is the right side.
okay, sure. But then the next point was like nearly identical, but subtly different. I couldn't understand what the difference is. And then it was horse generally have wider hooves on the right side. What is the difference? What am I missing? What is the difference between horses that train clockwise have wider hooves on the right side versus horses generally have wider hooves on the right side?
I think I might have misspoke on that part. I don't think horses generally have wider right hooves. Within our cohort, we found more horses with a wider right fore and hind hoof.
With a
Fore and hind hoof.
wider, okay, all right, thanks.
Yeah, so presumably, the assumption would be that this is functional adaptation to the loading. And it makes perfect sense to me that the lead leg is has the highest loading, because basically the animal vaults off that limb to get into the suspension phase. But you showed yourself that horses change lead rather. Sometimes they're on the straight, sometimes they're on the curve. Some of these horses are only 3 years old. When they train for half an hour a day, and when they race, they never go more than one time, or they never go 2 times around the track. So that's not a lot of curve running in their lifetime to cause this kind of functional adaptation.
I think maybe I'll start with the first part of the study, the first part of your question. Mostly it's like the leading limb doesn't necessarily be the one that is carrying more force. So I think there is a study that has people riding the horse and they're going in a straight line. What they found is that for the forelimbs, the leading and the non-leading, actually the peak vertical force is comparable, but for the hind limb is kind of different. So the non-leading limb is actually the one that has a higher vertical force. And this,
I'd be surprised by that.
It's Elton's, Elton's,
Yeah, okay, maybe galloping is different than cantering.
perhaps, and during that's during straight line. But what we found is that like on the curve, most studies found the outside limits actually having a stronger force, so they are actually having a higher vertical force. So that might balance out the two. This study, we trotted them in a straight line, so that movement asymmetry was actually like presented to us while they're walking in a straight line. Unfortunately, we don't have enough data to see the causal relationship as to like, is it because it's already wider, that's why they're doing that? Or it's because they are just trained to do it a certain way, so they kind of like don't want to use as much force in the side when they're not turning. We unfortunately can't do that, but what we found is that there is a difference when they're trotting in a straight line. And hopefully we can do something more to see what is the reason behind that. And the gait analysis was always done before the trimming. So we would assume that is something that they have adapted to for a long period of time. It's not because of.
I guess the other issue would be not necessarily force, but impulse. Because it could be a higher force because the foot's on the ground for a shorter period of time. And then the question is, what's the factor that's changing the morphology of the foot?
Yeah, that would be interesting to see. And I think with more hoof characteristics, we may be able to tell if it's like, oh, the inside or outside, the lateral, the medial is different, or they are creating a different loading pattern for all of these. And I hope that after we analyze more of the external hoof characteristics, we might have a better indication of what causes the difference and what is it trying to adapt to.
I have a question. When you say that their hoofs are trimmed, does that take away the asymmetry, not knowing anything about horses? Does that like get the hoofs back to the same size? And because it's adaptive, after trimming, do you see a difference in the asymmetry patterns?
Our photos were taken before that, so it is after 3-4 weeks of training, that's what we see. I'm not sure how the farriers decide how short they should be trimming the hoof, because the hoof is like a fingernail, right? So it might be interesting to actually do a pre and post before and after trimming to see if the movement asymmetry would be changed right after they say corrected to exactly the same between the left and right.
So the data that you showed for the results are based on kinematics.
Yeah, this
Not
this
on
like,
kinetic.
no, we do not have force plays.
But at the beginning, you showed a picture where you had the force in there.
Is it a different study? Is it a published study?
Yeah, but did you have the horse running over the horse platform then?
For this project, part 1, part 2, part 3,
No,
we did not
this
have.
project you didn't.
There are other projects with the one with the person riding there. They actually have force plates across, so that way they can actually measure the force. We do have I think I added it in here. So there is this study where they actually correlate the difference in the vertical displacement with the amount of peak vertical force changes. And this box is just where our horses were, like +10 to -10. And it would kind of tells us that the force difference is between -5.7% to +4.9% body weight. But for our project, we do not have force.
So how many horse platforms did you need to measure the forces?
I would assume.
Because you know, the origin of the Kister force platform the ones that we have down in the lab, was that some people wanted to measure the horses, exactly what you showed. And it was Wartenweiler that did that together with the owner of the Kister company. And then they had the horse platform and tried to do it, and the horse always missed the horse platform.
I mean, I used to do human studies. I know how hard it is to tell someone to land exactly on a force plate. So I would imagine it being super hard if we want a horse with their 4 legs land on one force plate without the other one kind of like adding force to. So we might need a lot. It also depends on how far apart you place them. So we have to be strategic if we actually have the funding to buy more force plates.
And another question, you said that you determine the vertical displacement with double integration of the acceleration. For that, you need the initial conditions, correct?
Because we are only doing it stride by stride. So we are just measuring the difference between the 2 peaks. So the initial condition doesn't really matter when we're just measuring the difference between.
When you double integrate, you need the initial condition.
We will need the initial conditions, but if we assume it, the moment that they land with their left hind foot is 0, then we will still have a relative curve. And because our variables of interest are just the difference between the 2 peaks, so it's like within the curve, the double integration or like drifting would not be a problem.
So you assume that the initial velocity is 0. Did you check whether that is true?
I did not.
We did that like, let me think about 2005, I think we did a great comparison where we looked at double integration of IMUs compared to kinematics. And we don't really, the only thing we're assuming is that it is sort of steady state locomotion over a few seconds, and then it matches very well.
Another question, you know, we were working a long time ago on spike shoes for sprinters in the 4x100 meters. And there is, you know, the number 1 and number 3 around the curve. And number 2 and number 4 is straight. And we had some test shoes where we increased the outside of the shoe. And you argued that the inside is the important thing.
When they,
We thought at that time the outside is important so that we basically banged the shoe.
there are also studies where they study like a banged track to see if that would, well, of course it would change the centripetal force and the normal ground reaction force relationship. We actually have a surprising finding because originally we hypothesized that the outside limb is gonna be the one that has a larger loading because of all the
That's
circle.
exactly.
Yeah, that in humans, in horses, when they are running around in circle, they did find that the outside limb is the one with the higher peak vertical force. But in our study, we actually find that the inside one is the wider one and the one that is actually carrying or weight loading or pushing off with more force on the inside. But this is when they are doing in a straight trot. So perhaps there are things that the horse is adapting to while they are running around the curve. Maybe still the outside limb that is doing the more force, but when they're trotted in a straight line, they prefer to use the other one to have a larger vertical displacement, which we imply to have a larger force loading and weight bearing. So yeah.
Any other questions?
there's always a question. I always thought that the inside leg is the leading leg when you turn. Is that correct?
Yep.
So I would expect that the horses lead with whatever when they are in straight. And as soon as they go into the curve, that they lead with the inside leg.
Yep, and that's what we saw from the slow motion video is when they are running on the straight, some of them go left lead, some of them go right lead, but when they are turning, the inside leg is always in.
So where are the races decided in the curves or in the straights?
Sorry?
On the finish, mostly on the straight.
The straights.
Yeah. And then they can swap again, they can switch to whatever leg they want.
We have time for more questions.
Yeah, I'll ask one. This might be a little bit silly, but do horses have like a dominant side? Like, do some prefer to run the clockwise versus the counterclockwise, and do they expect a screen there? Like that?
I asked this question a year ago to my lab mates and they tell me that, well, basically the only factor that determine whether they train, like a train race or clockwise or anti-clockwise is just where they are racing. There may not be like, I don't want to start a debate here, but if we want to, is like, is there a more natural way or is there a more right way? I think that discussion would be very close to like, is driving on the left lane or the right lane the right way? It's more, once they are adapted to it, how much can they adapt to the other direction would be a more like interesting factor than if they have like a dominant side.
But there is tests that you can do for laterality in horses. When they graze, for example, they put one leg forward or the other leg forward, and there's people looking into laterality versus movement symmetry and all these things. So there is some evidence that horses are also lateralized.
So they have a preferred.
Some do, and some to a higher degree than others.
Could that be the reason why there are two bins, like some have wider left side, some have wider right side, and then some not that, the ones that don't have no dominant side, but.
I think it's a multifactorial thing, and I don't know which of the factors will in the end the most contributing one, I don't know.
I mean, we can always go back and have someone check if they are left side or right side dominant, but how much of that is nature, how much of that is nurture, is because of the way they train, so that they already prefer the other side, like, all of these would all play a role into determining what they, like, how they walk in the straight. Any other questions? If not, we can thank.